Hey everybody, and welcome back to Algebra 2 Online. This is going to be just a third course review video here, covering just some more problems that I think are really important to know for the final. So, one of the things that I think is a little tricky in our trig unit is given trig graphs like this, writing the equation of them. So it's a little bit tricky because, for one reason, these graphs could technically have like two answers. So sometimes it's a little weird when you have like choice like that, and knowing like which trig graph to kind of pick for this thing. For this one, one like motivator for why I'd actually want to do this as a cosine is the one that's sort of, I don't really like the word start because it really does continue, but it's sort of, we think of it starting up at 1, because like in the unit circle, cosine's the x, and at an angle of 0, the x value is 1. So cosine sort of starts up and comes down like this. And then sine is the one that starts at the origin in a sense, and then kind of does that shape. We sort of have this one because we have if you have a peak or valley, I should say, as a y-intercept, then it's kind of a good indicator that you should probably go with a cosine. So I'm going to do this one as a cosine, but technically you could do it as a sine too. One of the first things I would figure out also is the period. So we can see that we go from 0 to 5. We're going to get a full period. So, the period for these sine cosine graphs is 2 pi over b. And then we know the period is 5. What we want to do is solve for b, right? So 5b is 2 pi, and that would imply b is 2 pi over 5. So we've got part of the equation already. We know the horizontal stretch compression factor scalar in there is 2 pi over 5. Then, we talked about before, like cosine really starts up, normally comes down and goes up, back up. Here we're starting down, so that means there's probably like a vertical flip going on. And we definitely are not at the normal height, right? We can see that this thing is centered at 3. And so it's shifted up. And if it's centered at 3, right, then you can see that the amplitude is different too, because the amplitude is, you're going 2 units up off of that and 2 units down off that. So this tells us like the amplitude is 2, and then the vertical shift is 3, and we know where there's a negative in there. So all this together, basically this function could equal 2, but a negative 2 really, because you have a vertical flip, cosine of 2 pi over 5 times like some variable, and then shift it up 3, right? No reason to shift it left or right, because then, you could write a sine wave that's shifted left or right to get this thing, but we tried to make it as simple as possible on this, so we were using cosine, just a flipped cosine to get to this point. So these are a little tricky, definitely. What you can do is sort of like, if you have like, 2 people you can like that you're studying with, someone can, put in, Desmo, something like this, get a graph, and then, ask someone what is the equation of that, and you have to kind of guess where it came from. So you can kind of make yourself even problems for these, and see, you can just make a sine wave or something, and then, just draw one, make it like fairly nice like this one, and then see if you could figure out what equation it was, and then you could test it, right, in Desmos or something. So good problems to know, for sure. All right, this one's going way back, but it's going back to a very important type of problem. So absolute value inequalities were one of the first, I think, more tricky concepts that we did. It really is like an Algebra 1 thing, but it's always a tricky one in Algebra 1, and so I always teach it again in Algebra 2, and it's a good one to know. Really, if you think about what this is saying, we have some absolute value function, right, which is going to be like some sort of v, and then we have less than some linear function, right? So if you're thinking pictures, right, you could have a few options here. You could have a linear function like that, and the absolute value could be less than the linear function, you know, between these 2 points or something like that. So you can get intervals. You could have a linear function like that, and you could have that the absolute value is never less than the linear function, so you could have no solution. You could have, you know, something like where the linear function is steeper here than here, and so you could have something where this absolute value is below the linear function from a point just going on forever and ever and ever. So you can get a few different cases of answers here for sure. But, you know, I wouldn't want you to graph it to solve it. I put in numbers specifically that are messy and kind of annoying to do with a graph, but we can just do it with algebra. So the way you do this is, first I would combine any like terms. So I would, you know, take this and move it over here, probably. Isolate the absolute value, basically. So we have 3x over 11 minus 12, less than 2x. And then we have minus 1.5 minus 4. So that's going to be minus 5.5, which is 11 halves, right? So we'll do minus 11 halves. Then the way these problems always worked is we basically get two problems to solve. So we have like our positive case, which you can just drop the absolute value. And then you have your negative case, where you don't want to drop the absolute value, or you don't want to just drop it, you want to negate everything in there. And then the one part that's really, really important to know is if the absolute value is over here on the left and you have a less than symbol, right? That is a specific and or thing. And if you ever forget it, I think the easy way to remember this is just take like a simple one, like absolute value of x less than 2 or something, right? What that would look like is, you know, absolute value is a distance from 0, and it's saying the distance this unknown is from 0 is less than 2 units. So over at -2 and 2, you would have open circles and you would shade in, right, like that. Anything in here is less than 2 units from 0. So that to me looks exactly like an and, right? If I'll have to erase all this really quick. If I flipped it, right, and I do the same idea, now I got -2 and 2, still open circles. If I wanted to say, you know, how much stuff is bigger than 2 units from 0, you know, anything like -2.11111, you know, all that stuff is bigger and going on is bigger than 2 units from 0. And if you go the other way, right, that is also more than 2 units from 0. So this looks like an or. So if you see absolute value on the left greater than 2, it's an or. If you see absolute value on the left and it's less than 2, think and. And so we have a and problem because of that symbol right there. All right? Very, very, very important part. It's going to completely change the answer if you don't get that part right. And then, you know, we just solve each inequality, and we have an and then, you know, it might be good to write the answer as an interval or graph it on a number line or something like that. So, you know, to get rid of the fractions here, I might multiply everything by 22 because then, you know, it's a common denominator between 11 and 2. And I'll just get rid of all the denominator, or the fractions, right? So 22 over 11 is 2. 2 times 3 is 6. 22 times 12 is 264. 22 times 2 is 44. And then 22 divided by 2 is 11. 11 times 11 is 121. I'm going to combine like terms, move the number over to the left, and then move the x's over to the right. And then just divide. So we get x is bigger than negative 143 over 38, which might be able to reduce, but who cares? And then over here, I might want to just distribute and then do the same thing, multiply by 22, just get rid of the fractions. And then, here I'd still probably just move the number to the left. And then add 6x to the right. I mean, that one's definitely going to simplify because they're both multiples of 5, but, oops, I just wrote equals. But I'm not going to worry about it. So, these two, things are basically, x is bigger than negative 143 over 38, and x is, so both of these are greater than, right? So x is bigger than negative 143 over 38, and x is bigger than 385 over 50. And so, it's an and, so you need to be concerned with the overlap, right? And so anything that's positive, if x is bigger than that, then x is bigger than the negative. So this part ends up basically having to be thrown out. We don't use that, right? And maybe just because they are, these numbers are multiples of 5, I'm just going to do on the calculator what that is. So actually it's just 7.7 exactly. So the way you could write the answer is either x is bigger than 7.7. You could do it the interval notation thing, open parenthesis there, and then out to infinity, and then open parenthesis. You could draw it on a number line. You can go 7.7, open circle, and just shade to the right, like that. So, if this had been an or, but it was not an or, this part would have definitely mattered. So this is a good example of one where you have to know that when it's an and or it's an or. And the fact that it's an and here, you need to be concerned with the stuff that works for both regions. If it had been an or, it could have worked for one or the other. All right. So this one, we haven't done one of these in these review videos, but another really important unit is our root function unit. And, one of the things that is weird about even roots, right, is the fact that they have restricted domains. So if you think of like a quadratic, right, or really any even polynomial, if you think about them, they have cutoffs in the y values, right? They don't attain these negative y values. So if you were to flip these, right, over y equals x and get the inverse function, you get cutoffs in the x. And that is, a big annoyance. We also had that these things, are not functions, right, when we flip them like this. So we had to also cut off the bottom. So these are probably the most irritating functions that we studied all year. They have the most issues, I guess we'll say. This one we're going to have to worry about domain, and the domains can definitely affect the answers and things like that. So the way I always wanted you to solve these is to just start and get rid of the root right off the bat. So, in this case, we got a 6th root, so we would really just need to do 4 raised to the power of 6, which is 4,096. And then we just have a quadratic inequality. So if you add, minus 4,096 to the other side, you're going to have minus 4,099, right? And, this thing has pretty nice roots. The roots would just be plus or minus. You would just, move this over and divide by 2, and you get the square root of that. So plus or minus square root of 4,099 over 2. And so, if you think about the picture here, we got the minus root, 4,099 over 2, and then you get the plus 4,099 over 2, something like that. We're looking for when is that quadratic bigger than 0, right? So we're looking for this chunk and this chunk. So it's one of those split cases. You're going to get an OR, right? So x is less than the negative, square root 4,099 over 2, or x is bigger than the positive 4,099 over 2. And that is halfway done with the problem, right? We need to check the domain, right? We need our answers to work for wherever this thing is defined. If you go and just take the inside, 2x squared minus 3, for even roots, right, we want it to be greater than or equal to 0. So we get another quadratic inequality that we got to deal with. The roots on this one are, you move the 3 over, divide by 2, you're going to get plus or minus square root of 3 over 2. Let's just kind of squeeze this in right here. You get negative square root 3 over 2, positive square root 3 over 2. This one is another one. It's like a greater than or equal to 0, so you're quadratic, like this. You're also looking for this region and this region. So it's another OR. You're going to have the domain, this is the domain, is anywhere where x is less than negative square root of 3 over 2, or x is bigger than square root of 3 over 2. And so now you just got to kind of take your answer, right, and you check it against the domain. And this one's a nice one because, you can definitely see this number is going to be a bigger number than this number, right? So the square root of like this larger number is larger, or in this case more negative. This one, it's actually larger, right? So the domain is sort of contained, even though it's an OR, it's sort of inside of this one, right? So anything that's less than that will already be less than that, and anything bigger than that will already be bigger than that. So you don't need to even really worry about the domain. Here, it does not affect it, but there are tons and tons of problems when we've seen them where it definitely does. This would be your answer without the domain really affecting anything there. All right, just one more problem here. Just verifying trig identities, another really important thing. We might have some big messy problem, and I think I'm actually going to do this too. We might be given 1 over cosecant squared theta, and then 1 minus cosecant theta, 1 plus sine theta. And we might be given in math or run into it just like in engineering or something somewhere that this whole thing equaled like 2, okay? Let's say negative 2. And if we were looking to solve this, right, we really want to try to simplify this side first. We don't want to have to deal with trying to, this is navigating how to figure out when this thing equals 2 is much harder unless you can simplify it. So verifying trig identities is a really important thing. So I want to start off and just basically show that this thing actually simplifies to cosecant theta, okay? So one thing I'm seeing right here, you've got a 1 minus cosecant theta, and you got a 1 minus cosecant squared theta. And, if you're thinking differences of perfect squares, this is actually nice because 1 minus cosecant theta is a factor of 1 minus cosecant squared theta. So what we can do is we can factor that top using a difference of perfect squares. 1 minus cosecant theta, 1 plus cosecant theta, 1 minus cosecant theta, 1 plus sine theta. And, that's nice because then I can cancel one of those. So now I have 1 plus cosecant theta over 1 plus sine theta. And then, nothing you can really do here except maybe try to write it in terms of, what cosecant is. And I think you will see where this is going once I do that. So cosecant is 1 over sine theta, right? And so we really have 2 terms here that I could combine, into one fraction. So common denominators, you're going to need like this to be written as sine theta over sine theta, which is 1, right? And so we'll do, sine theta plus 1 then over sine theta. Sine theta plus 1 over sine theta. And then if you look at this, right, if you just multiply top and bottom by 1 over 1 plus sine theta, 1 over 1 plus sine theta, that's like multiplying by a 1, but it's nice because this and this cancel, and this cancel, and what you would have left over, right, is 1 over sine, which is equal to cosecant theta, right? So that verifies the trig identity, which is really the problem. And just to kind of show you how we might use that again, like if we had this thing over here, maybe this is a trig equation that we run into. We now we'd have to go through all that, right? It's kind of tedious, but it is really important because it takes this thing, and now we're like, okay, well now the problem is just cosecant theta. When does that equal -2? Or if you think of this as this is 1 over sine equals -2, you could flip it and say, well, sine then, when does sine equal -1 over 2, right? And now you can just do unit circle stuff. So all students take calc. I can't be in those 2 quadrants because that's where sine is positive. I have to be in these 2 down here. And then you're just doing like finger trick kind of stuff. So you want sine of theta equal 1/2 really, because the negative is just the quadrants. And you do square root of fingers below over 2. So that has to be like your ring finger, that's like your 30 degree. So we basically get these 2 triangles right in here, here. So that is going to be, let's do it in radians, I guess. So theta is equal to, that's a pi over 6, and 6 pi over 6 would be pi, so you're going 1 more. So 7 pi over 6 plus 2 pi n, right? Because no restrictions on the domains and stuff. You can just keep getting that if you just keep going around and around and around the circle. 12 pi over 6 would be 2 pi, right? That'd be a full lap. We're 1 less. So that the other time you get it is 11 pi over 6, and then 2 pi n. And so, yeah, so any of these types of angles are where you're going to get a solution to this